Okay, so I've been tasked with trying to explain to you what this thing called big data really is. So I'll try to do that, and I'll also try to explain why this is relevant right now. So what is this thing called big data? Well, one way of answering that question is to say it's a hype. Because, well, I think everybody knows that here. It is a hype, a currently popular buzzword. So here's a graph that people in the tech community are very familiar with. It's the Gartner Emerging Technologies Hype Cycle. And according to this hype cycle, every new technology, it goes through this wave. So it starts here in the innovation trigger phase, when it's invented. If it becomes popular, it rises, and expectations, which is the vertical axis here, expectations rise. So here we find, for instance, quantum computing. They rise often too far. So they end up at something that's called the peak of inflated expectations. Right now, you see the Internet of Things is at this very peak. The peak of inflated expectations, it's problematic because there's only one way to go, and that's down. Down into the trough of disillusionment. So you end up down here, and here we have virtual reality this year. People are very disappointed with virtual reality. From the trough, however, that's a too negative position, so there is a climb up, something called the slope of enlightenment, and then you end up at the plateau of productivity. And at the end here you see speech recognition. It's on its way out this graph. So big data, you can see it. It's located in the middle of the screen approximately. It's just past the peak. It's on its way down into the trough, so we have trouble ahead. And there's still some time before we get to the plateau of productivity. And since big data is here, there's no doubt that it is a hype. But that's not all that big data is. So to try to understand this concept in another way, we can look at these one-sentence definitions. These are quite common, and there are many of them. One of the most popular is this one at the bottom, the 3 or 4 or 5 V definitions. That big data, it implies high volumes of data. It implies high velocity, so that data is created and it's transmitted very rapidly. High variety, so it comes in all kinds of formats. The veracity can be problematic, so you can't trust all big data. And there's also, some people say that you should also have the final V for value, which means that there is something valuable in this data. The problem with this definition and with all of these definitions is that these are relative definitions. You could argue that 10 years ago we had big data because it was bigger than 20 years ago. You could also say that it's not here yet because in 10 years, that's when we get the really big data. So these definitions, they are a bit unsatisfactory. So, because they still beg the question, so why do we talk about big data today? Why is it a hype today? So I'd like to suggest an answer that's relating big data to another hype cycle, and that's a hype cycle of machine intelligence. So in summary, what I'd like to propose is that a recent increase in data that we have seen, it has surprised us because it has allowed us to address some problems that we thought were very hard, that have been very hard, and that are important. So here I'll just present now for you a very brief and anachronistic and wholly incomplete history of machine intelligence. So here is the dawn of computing, ENIAC, oftentimes. This is the starting point for many people. And since then, we have tried to make computers smarter. Now, during the innovation trigger phase here of this hype cycle, we saw a lot of progress. So for instance, we saw Shaky the robot here. Let me show you Shaky. So here we see Shaky the robot. This is 1966. I don't have any sound. It's shaky. So he's trying to push a box in front of him here. So as you can see, Shaky is quite slow, but he does seem capable of some autonomous, goal-oriented and independent action. So in 1966, this seemed very promising, that maybe in a few months or a few years it would be possible to get these robots out into the real world to do real work out of the lab. So here he comes, and soon he will be pushing that box. That's his task. There, it happened. Okay, so that was 1966. So further progress now, that led to even higher expectations. So for instance, there was a significant moment when the supercomputer Deep Blue beat Garry Kasparov in a game of chess for the first time. Now computers beat people in chess all the time. But eventually here, the peak of inflated expectations was reached. And to be accurate, there have been many peaks of inflated expectations. So this is a bit anachronistic. But I have time constraints here. So here is one version of this peak from 1968.
The presence of Nomad aboard my ship has become nightmarish. Now it apparently means to return to Earth. Once there, it would automatically destroy all life. Hey, Nomad, stop! Nomad, this way. I am Nomad. I am perfect. That which is imperfect must be sterilized.
Error, 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 examine.
You are flawed and imperfect. Execute your prime function.
I shall analyze error. Analyze error.
Okay, so here you see, this is the Star Trek robot Nomad, and it's one of many fictional incarnations of a general machine intelligence. So as you noticed, this machine can navigate autonomously in the physical world. It can speak, and it can understand human language. It also has agency, so it has goals, ambitions, it wants to do things. And furthermore, and importantly, as you noted, it's capable of reasoning. It can analyze. So actually Nomad seems like a straight extrapolation from Shaky the robot here. So unfortunately, or perhaps fortunately in this case, the expected progress in machine intelligence, it didn't materialize. So almost half a century later, half a century after Shaky the robot now, we'd made only moderate progress. So let me show you now. Here's the annual World Robot Soccer Cup. So this is where the world's best robots fight it out in a game of soccer. Okay. Okay, so this failure to meet expectations, it has in fact led to a series of artificial intelligence winters, which are, that's another term for the troughs of disillusionment. And not only robotics has failed, but many different artificial intelligence research objectives have failed. Machine language translation, it failed for the first time in 1966, and it has failed many times after that also. And natural language understanding has also failed to deliver according to expectations several times in history. So what does all this have to do with big data? Well, it seems that massive these massive amounts of big data that are available now, that's precisely what's needed to tackle a number of these problems that have haunted machine intelligence. And so here are some examples. Well, language translation. This is one that I think many of you are already familiar with. It's available on the web. It doesn't work perfectly, but it's surprisingly useful nowadays. Another one is recommendation systems. In online bookstores, in music services, you get recommendations based on what the system knows about you and what it knows about the preferences of all its other users. It can make surprisingly accurate suggestions to you for further reading or viewing or listening. And targeted advertisements like this is really a major driver right now of big data. Here's a third example, which you might have heard of. It's a kind of a sequel to the chess game between Deep Blue and Garry Kasparov. So in 2011, a machine called Watson challenged the world's best players of the TV show Jeopardy! So in this clip I'll show you, Watson is a machine that's standing between the two world's best Jeopardy! Players.
Let's take alternate meanings for 200, Alex.
Four-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
Alternate meanings 400.
Four-letter word for the iron fitting on the hoof of a horse or a card-dealing box in a casino. Watson.
What is issue?
You are right. You get to pick.
Literary character, APB. 1,000, please.
All right, here is the daily double clue for you. Wanted for killing Sir Danvers Carew. Appearance pale and dwarfish. Seems to have a split personality.
Who is Hyde?
Hyde, yes. And anytime you feel the pain, hey, this guy, refrain. Don't carry the world upon your shoulders. Watson.
Who is Jude?
Yes. Watson.
Who is Michael Phelps?
Yes. Watson.
What is Event Horizon?
Yes. Watson.
Who is Grendel?
Yes. Watson.
What is The Last Judgment?
Correct. Watson.
Who is Lady Madonna?
Correct.
So you see, the machines, they defeat us now also in Jeopardy! So they're making progress. There's also progress in image recognition. This is very important in machine intelligence because it has to do with how we perceive the physical world around us. So for us animals, this is the major sensory input that we get. Here's on this topic of image recognition. This is the German traffic sign recognition benchmark. There is such a thing as a German traffic sign recognition benchmark. Yeah, and the goal here, it's to identify images like these, and for anyone or anything that is planning to drive in traffic, this is really important to be able to identify these reliably. So in 2011, that's the first time that a computer algorithm it achieved superhuman performance in this test. So it performs better than people. So since 3 years back, machines are better than humans also in reading traffic signs. And very recently, actually this year, machines outperformed people in the detection of breast cancer. So in this image, here you see these circles. That's mitosis, that's cell division in breast cancer in a microscope image. The green circles, that indicates where this algorithm succeeded in identifying mitosis, and this orange and blue, those are things that it got wrong. But people got it worse. So machines now, in a scientific paper that's been recently published, they now beat people also at this task. Also on image recognition, I just stumbled across this the other day. Obviously, police in Dubai, they're going to get these Google glasses, and simply by looking at people, they will be able to recognize their faces and then recognize these potential criminals from, well, registered criminals. So that's a bit spooky, I think. But face recognition is that good now. Okay, so one more example, natural language processing. Robert talked about that previously. It has seen a remarkable progress now, also due to big data. So if you have a smartphone, you can do these things with your smartphone already today.
Make a reservation for 2 at an Italian restaurant at 8 o'clock tonight.
I found 2 tables for 2 at 8 p.m. Tap the one you want to reserve.
What airplanes are flying over me right now?
Checking. All right, here's what I got.
What are some action movies out?
I found quite a number of action films.
Is The Hunger Games Catching Fire worth watching?
Rotten Tomatoes gives The Hunger Games Catching Fire 89% rating.
Show me the trailer.
Here's your trailer.
Move my 10 o'clock with Ed to 11.
Okay, I'll make that change to your event.
Do I need an umbrella on Friday?
There's no rain in the forecast for Friday.
Give me directions to the nearest gas station.
Getting directions to Chevron stations.
So you can have these, you can have hour-long conversations now with your machines. Okay, so as a final example, take a look at self-driving cars. All respectable car manufacturers, they produce self-driving car prototypes now.
So while we take in a ton of information using our sensors, it's our software that really processes all of this and differentiates between objects. All these objects are visible on the laptop that the safety drivers use while testing the vehicles. Based on what the vehicle senses and processes, these objects will be represented by different colored boxes. Cyclists will be red, pedestrians yellow, and the vehicles will appear as either green or pink. These boxes demonstrate the processing that takes place within the software. And think about the complexity here. People look different, cars have different shapes and sizes, yet despite these nuances, the software needs to classify these objects appropriately based on factors like their shape, movement pattern, or location.
So obviously, these self-driving cars, they really work now. And they're almost here. Volvo, for instance, they have planned to introduce 100 self-driving cars in the Gothenburg region in 3 years from now, in 2017. So this is very much happening. So as I've already indicated, there's a common underlying theme to all this, and that's big data. So the amounts of big data that are being generated now, it's stupefying. Here's a graph over the total global data traffic in mobile networks, and you can see it's almost exponential. Here's another graph that is produced by a company called Domo. It's another way to look at what is being generated. So every minute of every day, obviously, all of this is being produced. I mean, take a look at that. 200 million email messages every minute. And 72 hours of new video uploaded to YouTube every minute. And there's 2.4 million Facebook entries, 500,000 photographs. It's such enormous amounts of data that it's incomprehensible. And so what's the basis, the technology behind this? Well, the most obvious one is, of course, the internet. This is has been growing steadily, and this is a picture from, it's been hanging at the New York Modern Museum of Art, the NOMA. It was released recently, this picture of the internet. It looks like something from the Hubble telescope. The Internet of Things is another thing. That's another important development that has created all this big data. So this is connecting lots of new devices to the internet. So of course laptops and stationary and cell phones, they're already connected, but now we're connecting cameras and cars and security systems and factories and power stations and healthcare equipment and household appliances, and you can connect your toothbrush, and you can even connect your pets. There are methods to connect your cat to the internet. And so this is digitizing much more and more of our daily lives and the world we live in. And so not only production and transportation, but also storage capacity and processing power has increased. It's continued to grow rapidly. So this is Google's data center in Iowa. And in these data centers, in order to manage these large volumes, they need to employ new technology. So two buzzwords that are often mentioned in conjunction with big data are Hadoop and MapReduce. So I won't go into detail on what they are, but they make it possible to store and to process data in a distributed manner so that you can manage this onslaught of data. So a lot of the fundamentals of big data, it has to do with infrastructure. It's possible to create and to transmit and process and store larger amounts of data now than ever before. But there's another important field that I haven't mentioned yet, and that's machine learning. So rather than creating or enabling big data, machine learning exploits it. So it uses all this big data. So one central problem in the applications, almost all of them that I mentioned previously, it's the problem of classification. So for instance, here in image recognition, we'd like a machine to understand what it sees. And one test is to let the machine make this mapping between these labels, these names, and these pictures. So the problem for the machine is that the machine doesn't see what we see when they see this pictures. They see this. This is numbers representing colors in a pixel map. And so how would it be possible to identify from these numbers and colors to identify these kinds of labels? If you have a simplistic rule, you would say perhaps, okay, a black and white kind of pixel map, that's probably Muhammad Ali, but that doesn't work because that's also Sugar Ray Robinson there, and Muhammad Ali is there and there. So you need something more complicated than this. And this problem, it's difficult, it's important, it's also similar to other problems like speech recognition. Here, instead of the pictures, you have words. Someone says Muhammad Ali, and then you have more or less the same problem they have to solve here. And translations are also similar in this sense. So one solution to this is to use low-level concepts to define higher-level concepts, and which in turn can be used to classify an image. So for instance here, pixels, they can be aggregated into edges, which in turn can be used to define more complex shapes. And in the end, you can use these. When it comes to face recognition, you can use these facial archetypes to define faces. So you could say, okay, I have 20% of A1 and 12% of C3, and look, it's Sugar Ray Robinson. So that's approximately how it works. And today there are many algorithms that can learn these concepts more or less by themselves if they only have access to data. And these algorithms, they go by names such as neural networks and Bayesian classifiers, support vector machines, and hidden Markov models. And the hottest topic right now, that's algorithms that enable what's called deep learning. And it's called deep because you use multiple layers of abstraction, just as in this slide. However, the amount of data often trumps the choice of the algorithm. So here is a graph from a paper from 2001 where each line here represents an algorithm and how it performs. The accuracy is here on the vertical scale, how it performs at different data set sizes for learning. And it turns out, if you look at this graph, that it's better to have a poor algorithm with a lot of data than to have a really good algorithm. So a poor algorithm with a lot of data, that's up there. That's better than to have the best algorithm with not so much data. So there you have it again, big data, very important. So now let's return to the hype cycle. Yet another indication that we are actually out of the trough of disillusionment in machine intelligence is that it's made the headlines recently. There was this influential book up there in the right corner, The Second Machine Age, by two researchers at MIT in Boston, Brynjolfsson and McAfee, and it received a lot of attention, and they predict that computers will soon replace humans in many jobs. And some months later, the Swedish Strategic Research Foundation, they came out with a report, the green one there, where they predict that in Sweden, half of the jobs will be automated in the next 20 years. And this was widely published in media this summer. So we might expect that we are approaching the plateau of productivity, but instead there are some worrying signs that we might be heading towards a new peak of inflated expectations, because there are a number of books and articles that have been published on something that they call the intelligence explosion. And these books, they predict that a future where machines, they don't become just a little bit smarter than us, they become immensely smarter than us. They become virtually omnipotent, like gods. And I have to mention in particular, there's a Swedish philosopher, Nick Boström. He's at Oxford University, and he's received worldwide attention with his book, Superintelligence, over there, in which, well, I think everyone has to agree that it's wildly speculative. I think he would say so too, because in the book he explains in detail how and why supercomputers, these really powerful computers, will end up exterminating the human population. So it's a kind of serious, it's a serious study, and it's been reviewed in favorably also in the Financial Times, in The Economist, The Guardian, and other papers. So these ideas are quite seriously taken. So I think that this might be an indication that we are heading towards a new peak of inflated expectations. So to conclude, I'd like to say this, that big data, it's part of a greater technological evolution, which, at least from the perspective of a country like Sweden, it can be viewed like a big wave. It's a major force, and we really can't stop it. So in this talk, I've tried to explain where this wave comes from, and Robert Kirkpatrick here, he spoke of how it can be used for good. There are other benefits, we will hear about them later today, and there are also costs and there are risks that both Robert spoke of and that we will hear more of, I think. But I think, therefore, that one of the most important questions for us as people, as individuals, and as a society is how we position ourselves with respect to this wave. We can't stop it, but we can perhaps surf it. Thank you.
Thank you. Thank you, Pontus. Some very interesting and somewhat scary perspectives in there as well. One thought came up when we're depending on this machine intelligence and all that stuff and the network of systems and servers, how sensitive is it to disturbance or manipulation or anything? Is there any?
I think that there are big risks. Talking about the security aspects of this, I think that there are significant risks. There is a lot of, already today, we are not very secure in our information systems, and big data systems, they are notorious for their vulnerabilities. I think that there's a international database for vulnerabilities in software. It's called actually the National Database because it's American, but it reports some 76,000 vulnerabilities in software since the mid-90s. So there's a lot of vulnerabilities. Every year we discover more vulnerabilities. So I think that keeping this safe, it's like physical safety. You have to keep. People can come into your house, then you buy a lock, but they can still break into the lock if they really try. So it's kind of a trade-off. I don't think we will ever get rid of that problem.